Hi everyone, this is Mr. Cervone. Welcome to my math channel. To the left is a diagram of a residence. The line below the house represents the surface of a lake. Assuming the lake is perfectly calm and that it is a calm day, what would you see in the surface of the lake? Well, what you would see is the building itself with the mountain and the sun upside down. Now, this type of observation is actually a transformation, mathematically speaking, which is a type of transformation called reflection. And in today's lesson, we will discuss what are reflections and what the definition of transformations and reflections are. So let's get started with the definition of transformations. So a transformation is some change to an object in the plane. Now here's some examples of transformations, and we already saw one image before, but for example, you can see the reflection here of the ice cap on the mountain in the water, or for example, here you see the symmetry of a dog's face, and there's so many real-life applications that can be attributed to transformations. But today, let's discuss reflections. And here's the definition. A reflection in the plane over a given line K is, number one, if P is not on line K, then P prime is defined so that K is the perpendicular bisector of the segment from P to P prime. And secondly, if P is on line K, then P is its own image. Now, what does that mean? So let's get started drawing a line K first. Then we have a point P which is not on line K. So let's assume we have a point P here somewhere. So that means that P prime is defined so that K is the perpendicular bisector of the point P and P prime, that segment that defines P and P prime. So that means that if P prime is located on the other side of line K, then if you draw the segment joining P and P prime, so I'm going to draw it dotted here, then what happens is that K now becomes the perpendicular bisector of the segment P and P prime. Okay, so this is perpendicular and these two segments are congruent. So that is actually the first part of the definition of a reflection, okay? Now, if the second part, if P is on line K, so you have P over here. Now, if you reflect that point P about line K, then P is its own image. Okay, so that means that in this case, that point is going to be P, but also equal to P prime. It's the same thing. Now, there are some words here called image. So let me define this first. So in this case, P is called the pre-image. So here we go. And P prime is called the image. So it's kind of like when you look at yourself in the mirror, you're the pre-image, but inside the mirror, you see the image of yourself, okay? And in the second part, we have that the pre-image is equal to the image itself. Now here's a more precise definition of transformation that relates image and pre-images. A transformation is a one-to-one correspondence between two sets of points, S and S prime, such that every point in set S corresponds to one and only one point in set S prime called its image. And every point S prime is the image of one and only one point S called the pre-image. So basically, that is the precise definition of transformation, that you can only have one image or one pre-image that correspond to each other. Now, it turns out that when you transform a point, you can also transform a figure or an object, and the same thing with the reflection. For example, let's say you reflect an entire object here over a line K. So it turns out that this object is going to be exactly the same. Okay, maybe I should move that object a little further to make it a little bit more precise, because that is going to be, again, the perpendicular bisector. So you can actually reflect not just a point, but you can also reflect an entire object over a line. And in the next coming lessons, we will also learn that you can actually reflect an object or a point, not just over a line, but even over another point. So just bear with me. Now, what do you notice here? When you reflect an object, what happens to the shape and the size of the object? Well, it turns out that the shape and size will stay the same after a reflection. That is the definition of rigid motion. The rigid motion in the plane is a motion with an altering size and shape. So we just learned that one of the rigid motion is reflection, okay? Or reflections. Now, it turns out that there are other rigid motions, okay? For example, when you translate something, so let me call it translations, okay? Then we have also rotations. And the question is, what about dilations? Are dilations a rigid motions? As a matter of fact, it turns out that dilation is actually not a rigid motion, okay? Because it does alter the size and the shape of the object. So in today's lesson, we'll just focus on reflections, and in the next coming days, we'll focus on the other rigid motions, namely translations and rotations. Now, how does rigid motion relate to congruence? Well, let's think about this. If, let's say, I call this object A and this is object B, it turns out that rigid motion also states that here in this case, object A will be congruent to object B. And that is a little bit more of an accurate definition of rigid motion. So for example, is triangle RST congruent to triangle MNO? Well, by the definition of congruence, we need to find a rigid motion that maps triangle RST onto triangle MNO. And as a matter of fact, it does occur with a reflection. As you can see here, you're reflecting one of the triangles, for example, triangle RST over line L. Once you reflect it, you end up with triangle MNO. And it turns out that they are congruent because we can see here that the corresponding sides are congruent and the corresponding angles are congruent. So for example, we could use SAS postulate to prove it. And as a matter of fact, with transformations, there are also proofs involved and also constructions involved, okay? So here's an example of how rigid motion works when, let's say, a triangle ABC is reflected over a line such that you generate triangle A prime, B prime, and C prime. As you can see, if you, let's say you move a point, the triangles will always be congruent because that is a rigid motion, okay? Even if they overlap, the triangles will always be congruent. Now, what happens if you move this line here, let's say to the right and to the left? Well, we learned that these have to be perpendicular bisectors, all these points that connect. So for example, A and A prime, B and B prime, and C prime, if you draw segments, the line becomes the perpendicular bisectors of those segments. Okay, so if you move this line here, for example, like this, as you can see, the distances will always be the same. It has to preserve the bisector part of the definition, okay? Okay, so let's get into the notation of reflections. So the geometric notation for reflections is a lowercase r followed by a parentheses, and in the parentheses, for example, goes the point or the object or the triangle or anything that you're trying to reflect, and that is equal to, let's say, P prime. So keep in mind that this is now the pre-image, and P prime becomes the image of the object that you're reflecting. Now, if you take the previous example, in which triangle RST is being reflected over a line to create triangle MNO, How can we represent that as a reflection? Well, if you want to, you can reflect each individual point. For example, call it R point S or R of S. And now we want to put lowercase l because we're reflecting over line L. So that creates point N. Then we have reflection over line L, let's say of point R. So here we have point M. And similarly, reflection over point L or over line L of point T, that is equal to O. We can actually summarize this entire reflection as reflecting over L, let's say triangle RST, which is equal to the image of RST, which is M and O. So here we get triangle M and O in that same order. So we have to be careful to keep the same order, okay? So if we start with R, then the corresponding point is M. And then we have S corresponding N. And then finally we have T corresponding to O, okay? So that's how you denote reflection in geometry, okay? So let's look at an example now. So here we have an image, and you can clearly see that these are triangles. For example, triangle ABC reflected over line K to get triangle AED, okay? So for number one, what is R sub K of E equal to? So if you look at this, E is reflected over K, or B is reflected over K to generate point E. So in this case, it's just B the answer. Now, you can also reflect the image to get to the pre-image as well, okay? For number two, what is the pre-image of point D under the reflection? So you can clearly see we're reflecting it. So again, this is the perpendicular bisector, so the answer is point C. For number three, what is R sub K of A equal to? And here we have the same point A, because in this case, the image is equal to the pre-image. And finally, for point 4, so we have BE is equal to 15. What is the distance from B to line K? Well, since that's the perpendicular bisector, we actually divide 15 divided by 2, and the answer is 7.5, okay? Okay, so let's look at another example where we can use reflection in a real-life application, such as when you play mini golf. Bounce ball G, offside D, and then offside K to get the golf ball in the hole H. Where should you aim the golf ball? So obviously, let's say you aim somewhere on side D, is going to bounce back here and go back to H, right? So that's the goal, but where will you aim? That's the initial path here. Where will you aim? So in this case, we kind of have to construct the reflections, okay? And we're going to learn more about constructions here later on. But the first thing is, for example, here, get a ruler. And let's say you want to work backwards now, okay? So always work backwards in problems like this. So let's say you draw the reflection of point A, okay, over line K here. So let me label that H prime, okay? So keep in mind again that this is perpendicular, and the segment that defines H and H prime is now bisected by line K. So K is basically the perpendicular bisector. Now we want to reflect H prime again, and let me use a different color. Let me reflect it over line D, okay? So we're gonna reflect this over here like that. Okay, so now we gotta have the same distance here. Okay, so ideally you want to construct these. So we're saying that this distance and this distance are congruent, okay? Okay, so let's do this. So this is a little bit more accurate. Let's draw arrows. So we're saying that these two distances are congruent. So that one now becomes point H double prime, okay? Okay, so let's now draw how we should aim the ball here, okay? So again, you get the ruler and you align point G and H double prime here, okay? Okay, so let's say you aim the ball this way, as if you're aiming to H prime. So let me draw it dotted. So what happens here, if you aim it this way, it would actually bounce back to, let me draw a better arrow here, it would actually bounce back as if it's aiming to H prime now, okay? So what happens here, the ball goes this way, as if it continues all the way to H prime. So at this point here, it's going to bounce back and actually go to hole H, okay, like this. And that's basically how you solve the problem. So you want to aim over the reflections, basically, in prompts like this. But again, you always work backwards. So I guess you can see where construction comes into play here, okay? How do we, for example, get these two distances to be exactly the same? For example, you can put the compass at this point and measure the distance from this point to H prime and then draw a circle in this manner. But this is now the center, okay? So that's how you want to do these types of constructions. So if you have problems like this on the homework assignment, I would highly recommend for you to use your compass and straight edge, okay? But anyways, that's basically it for today's lesson. Tomorrow we will see how we can apply reflections in coordinate geometry as well, okay? So again, thanks for watching and have a fantastic day.